Good evening. We are out of integrals. Now, we're still going to be using integrals, but that's no longer going to be the main focus. We move on to the branch of calculus known as series analysis. That's a series. An infinite series is the sum of an infinite number of terms. Ultimately, the goal of this topic, series analysis, is to get to representing any function as a power series. And there's a few things we need to do. Functions can be represented as power series, but they have an interval of definition called an interval of convergence. It's where it's a valid expansion. So we need to know, when does a series converge? What does it mean for a series to converge? How do we determine whether a series converges? For that, we need to actually know, well, what the hell is a series? What does it mean to sum up an infinite number of terms? The idea behind that is we take a look at the partial sums, the sequence of partial sums. We take its limit. That's an infinite series. What the hell is a sequence? That's where we start. We start by defining sequences. This will then allow us to delve into the study of power series. Generally speaking, a sequence is just a collection of numbers. It's really all a sequence is. Sequences can be finite. More often than not, they're infinite. The vast majority of sequences you're going to run across, you cannot define a general term. Here's one such sequence. We cannot write a formula, call it a sub n, to determine what the nth term of that sequence is going to be. What is that sequence?
Pi.
That's the sequence of the digits of pi. Pi is irrational, meaning there's no way to determine what the nth digit in pi is. You also have some sequences that are what's known as defined recursively. These sequences, they're going to give you the first couple of terms of the sequence and then tell you how each term is calculated based on the previous terms. The most famous recursively defined sequence is the Fibonacci sequence. Oh dear. I think it's that. Actually, no, I think it's 1b and 2 n's, actually, now that I look at it. No? Two C's. There are two ways it's commonly defined. That's one way. Formula is the same, it's just what two values do they give you. I go with that definition. I don't put 0 in as a Fibonacci number. The sequence, defined recursively, each Fibonacci number is the sum of the previous two. There is a general formula for f sub n that you can find. That's beyond the scope of this course. There is an important result, and I'm fairly certain it's going to be your next group assignment. Showing that the limit of the ratio of the terms of the Fibonacci sequence is what's called the golden ratio, which I think I discussed. One plus root 5 over 2. So that's going to be your next group assignment to actually prove that limit. This is important. Fibonacci numbers are everywhere. Next time you see a sunflower, count the seeds in one arch. Actually, count the seeds in each arch. It will always be a Fibonacci number. The conch shells, the distances between each chamber, right, the size of each little chamber, always a Fibonacci number. I think it was the Greeks, probably also the Romans, when they did their constructions, used the Fibonacci numbers for their symmetry. Which of course means that phi is the most common number in the universe, not pi. In fact, no, pi is fairly common, but you normally think pi, spheres, circles, right? There's no such thing as a perfect sphere in the universe. You never actually see a circle in nature. You never actually see a sphere in nature. This topic is probably going to be the most challenging thing you do in math if you're a non-math major. Because it's a completely different way of thinking. This is now abstract. Generally, I'm going to give you a series, and I'm going to say, does it converge? And that's what I'm going to ask. There are 7 tests that we cover, plus 2 special series of 9, to determine whether a series converges or diverges, and your job is to figure out which test you have to use. The only way to do it is to do enough of them where you start to recognize patterns. This test is used whenever the form looks like this. I also won't always be nice enough to give you the series and summation notation. Right, so in other words, it may look, I guess we'll find back to here. So I could give you the series written out as a sum of values, and then it's your job to determine summation notation, a general formula. Again, this requires pattern recognition. So we're going to get some practice. We're going to be given several sequences, and we're going to be asked to write a formula for the nth term. Generally speaking, there are a lot of ways you can write the formula. Whenever you write a formula for a sequence, you have to have a domain. Right? So the Fibonacci's, the domain is n greater than or equal to 0 or 1, depending on how you're looking at the definition. Right? But your n, right, your quote-unquote variable, will always be an integer. That's the nice thing here. Right? So it doesn't make sense to say what is the pi Fibonacci number. Right? That doesn't make sense. But I could ask what is the 8th Fibonacci number. Right? Then I'm looking for f sub 8. The sequence of terms, 1/2, 1/4, 1/6, 1/8, so on and so forth. So what is the formula for the nth term?
F first plus f n minus 1.
Do not do it recursively. So if I give you the sequence, I just say, what is the 20th term? That's what this formula is going to be.
Is f first plus f 19.
You said f?
Well, like whatever the a.
Yeah, so again, you're trying to define in terms of previous terms in the sequence. Don't do that. So look at each term individually. First, you have to decide, where are we starting? Do you want to start with n equals 0? Start with n equals 1? 1's generally where we start. So first term is 1/2. Second term, 1/4. Third term, 1/6. Fourth, 1/8. What would be the fifth term? The sixth. So notice, every term's a fraction with 1 in the numerator. So there's a good place to start. What do you notice about the denominators? They're the even numbers, aren't they? How's an even number defined? You just said it, multiple of 2, which is what? What does it mean to be a multiple of 2?
You have 0 as a, I don't know how it's called. When it's divided by 2, it's 0 like left.
Right. Remainder, when you divide by 2 is a remainder of 0. There's another way of saying that.
Divisible by 2?
What does it mean to be divisible by 2? 2 times a number. For n greater than or equal to 1. With this, if I now say, what is the 832nd term? You could easily figure it out. It's 1 over 2 times 832, which would be, what, 1664? 1 over 1664? About here. 1/2, 2/3, 3/4, 4/5, so on and so forth. Let's call this b sub n. Well, each one's going to be a fraction, right? Again, you need to decide a starting point. Let's say 1. So look at the numerators first. Numerator of the first term is 1, right? So numerator of the second term. Numerator of the third is 3, right? So the numerator of the nth term would be n. What about the denominator?
Plus 1.
And there's your formula. Call this C sub n. 1, negative a half, a third, negative a fourth, a fifth, negative a sixth, so on and so forth. Now let's start at 1. What is the first thing you notice about this sequence?
It goes from a positive to a negative, to a positive to a negative.
That has a special term. It's called alternating. So it alternates between positive and negative. How are we going to represent that? So first term is what? Positive or negative?
Positive,
Second term,
negative,
third term,
positive,
fourth term.
negative.
Specific, so all the odd terms are going to be positive, all the even terms are negative. I think we'll represent that.
Something with power? No.
It's definitely going to be a power. be negative 1 to some power. What power? There's more than one right answer. So even is positive, odd is negative. What happens if we raise a negative number to an even power?
It's positive.
What if it's raised to an odd power? So if the odd powers, or the odd terms are positive, can't be that. What if I have 1? Now all the odd terms are going to have an even power, right? All the even terms are going to have an odd power. Perfect. You could also use n minus 1. That's more common in certain texts than n plus 1, but they're both valid. Now, what about the denominator? It's just n. Right, so that'd be our general formula. Point 0.9, 0.99, 0.999, 0.9999, so on and so forth. And then we're soon starting at 1. So what do we think? So how could you write 0.9?
So maybe just plus 0.09 every time, or no?
Well, not
Like,
0.09.
every time 1 0 adds up.
So how would you represent that?
That is 0.9 plus 0.09 multiplied by 10 minus 7, something? No? So like every time it increases?
0.09 times 10 to the minus 10 is going to make it smaller than 0.09, so I wouldn't use that.
Yes.
So there's going to be a problem with this. Right, so it's going to be 9 times 10 to some negative power. So for the first term, this is where the problem comes in.
And plus 1.
It's 0.9 times, it's 0.9 plus 0. And there's no way to get 0 out of that. For the second term, if you want to do that, and greater than equal to 2, that would work. No, it wouldn't either. Because if I go to the third term, it'd be 0.9 plus 0.009, which is 0.909, not 0.999. Geometry track.
Would it be 1 minus 1 to 10 to the negative n?
You don't need the 1 in front of the 10 in that case. Right? It'd be an implied 1. Yeah, it's 1 minus 10 to the minus n. 4 and greater than equal to 1. So what do? We started off easy. Even that was easy. Okay, now we're starting to get a little more patterns, a little bit harder to see. Let's go with -1, 0, -1, 0, 1, so on and so forth. This is interesting. to make this clearer, what do you think the term before that one would be, if there was a previous term? What does that look like?
Sine.
Looks like sine. But sine of what? You could also use cosine with a slight adjustment.
-1. Cosine -1, like to shift to the right side or no?
You wouldn't use cosine of -1. Right? You're going to adjust the variable a little bit. There's actually two ways you could adjust it. So I've written both because they're both equally valid. So sine of what? So when is sine equal to 1? In radians.
Over 2.
Where is it equal to 0?
0.
True, but you don't want to go backwards. So pi would work. What about -1?
-pi/2? Or no?
Again, technically yes, but that comes before pi.
So 3 pi/2?
3 pi over 2. 0.
2 pi.
2 pi. What do you notice about all of those? They're multiples of pi over 2. Sine of n pi over 2. Using cosine, there are two ways we can define this. We can use the same argument. Right, because cosine is 0, 1, or -1 at multiples of pi over 2. But we now don't start at 1. You could start at either 0 or 2. Or 4. If you wanted to stick with 1, then this argument has to change. And I think this is where you were coming from. N minus 1 pi over 2. Right? Or you could use n plus 1, that would also work. Yeah. Either one of those are valid for this sequence. That one was a little bit trickier. So maybe the trickiest of the bunch. 2 9/4, 64 over 27, 625 over 256, so on and so forth. Well, first, to help us with a pattern, why don't we write 2? That's 2 over 1. Two over 1. Two to the first over 1 to the first. Nine over 4. Well, 9. Three squared over 4, 2 squared. $64 over 27. So 64. 4 cubed, isn't it? What about 27? 625. What is it? 5 to the 4th. 256.
4 to the 4th.
So this is the first term, second term, third term, fourth term. What's the power going to be for the nth term? So what's the exponent?
Oh.
Just n. Now the question is, what are we raising to the nth power?
N plus 1 over n.
There's a general formula. So you need to be able to pick up on patterns. Now we need to discuss the idea of a limit of a sequence. When we talk about limits of sequences, unlike with functions, there's only one limit we actually care about, and that's as n approaches infinity. So what is the sequence going to do long term? This is also known as what is the sequence converging to. definitely not that. Those two mixed up. For all epsilon, there exists an n. Yes, that's better. And that should be capital N. This is the definition of the limit of a sequence. This is called the epsilon n definition. Depending on who you had for Calc 1, since none of you had me, you probably didn't see it. That definition should look familiar. Some slight changes, but that's the same definition as the definition for the limit as x approaches infinity of f of x. If you actually look at the formal limit definition, it's an epsilon delta definition. Working with that definition is a massive pain in the butt. Trying to find the limit of a sequence is the exact same as trying to find the limit of f of x as x approaches infinity. There's literally no difference. That means all of your rules from Calc 1 on limits apply. L'Hopital's rule. Sum, difference, product, quotient, power, radical. The composite function theorem. And the one that is most often forgotten. Squeeze theorem. Hope you remember them. I want to find the limit of that sequence, so the sequence defined by that term. When talking about sequences, I'm probably going to leave out the n approaching infinity. Because again, it's understood that's what we're looking for. You may also see it written this way. So represent a sub n converges to L. So what is that limit? This is an easy limit.
Denominator equals to 0. Denominator equals to 0.
Well, it's infinity, and for n, would stuff in the numerator and denominator cancel
No, that's not how that works. Right. Technically, you're also not plugging in infinity because it's just a concept, not an actual value. But if you looked at it that way, this would be infinity over infinity. It's called indeterminate. Three ways to approach this. First way is using algebra. Second way, infinity over infinity is one of the proper forms for L'Hopital's rule. You could use L'Hopital's rule. Or you can just determine this limit by inspection. How does the numerator behave as that approaches infinity? Isn't it just 5n squared? For very large n, that plus 13 doesn't really make a difference. Well, that n squared dominates, doesn't it? N squared dominates n for extremely large n. Right, 10 to the 100th. 10 to the 200 versus 10 to the 100. If you do 10 to the 5 times 10 to the 200 minus 4 times 10 to the 100, there's not that much of a difference. It's negligible. That n squared term dominates. Same argument for the denominator. That 3n squared term dominates. For large n, that function behaves as 5/3. Right, 5n squared over 3n squared, which is 5/3. That's your limit. Which, by the way, you would also get if you used L'Hopital's rule twice. First application would give you 10n minus 4 over 6n minus 95. Second application would then give you 10 over 6, which is 5 over 3. Now 8n squared minus 3 over 2n plus 5. What is that limit? Again, you can use L'Hopital's rule. You can also just inspect it and know what the limit is. So for very large n, how does that function behave? So again, think of 10 to the 100. 8 times 10 to the 200. Subtract 3. Is there really going to be a difference? It's a negligible difference, isn't it? 2 times 10 to the 100. Add 5. It's going to be a negligible difference, isn't it? So doesn't this behave 8n squared over 2n? Which is what? How does that simplify? 4n. What does 4n do as n gets large?
It's larger.
That one's infinite. In which case, we'd actually say that sequence diverges. Three n plus 7 over n cubed minus 2n minus 9. What do we think this limit's going to be? So again, how's it going to behave for large n?
It's going to be 3 over n squared.
Yes.
As n gets large, what does that do?
Smaller.
Specifically smaller to what?
Just
That limit's 0.
Yes.
So there are going to be times when you actually don't care what the sequence converges to, you just care whether it converges or not. The monotone convergence theorem. This theorem is so important gets its own abbreviation. Much like the fundamental theorem of calculus has its own abbreviation, the FTC.
Yes.
If your sequence is bounded and monotonic, it converges. What does that mean? There's a lot of terms in there. What does it mean for a sequence to be bounded? Well, it's bounded above if there is some value big M such that every a sub n is less than or equal to it. In which case we say that that big M is an upper bound. Bounded below if there exists some value, call it little m, such that a sub n is greater than or equal to little m for all n. So every term in the sequence is larger than that little m. Right? Then we say that little m is a lower bound. So let's think of it. Are bounds unique? And so let's say I have a sequence, and you know that 8 is an upper bound for it. Is 8 the only upper bound? If we look back at the sequence of the digits of pi, what would be an upper bound for that? That would be an upper bound. Right? Because no digit of pi is going to be larger than 9. Based on what we mean by digit. Right? Digits are 0 to 9. Is 9 the only upper bound? No, what else is an upper bound?
Plus infinity.
Well, again, infinity is not a number. If you're saying there's an infinite number of upper bounds, you're correct. Any number larger than 9 would also be an upper bound, wouldn't it? Bounds are not unique. Lower bound. Zero would be a lower bound, right? But again, anything less than 0 would also be a lower bound, wouldn't it? However, if a sequence is bounded, it will have what's known as a least upper bound, right? So it's going to be a smallest number that serves as an upper bound. In the case of pi, the digits of pi, that'd be 9. Right? There's no upper bound smaller than 9. We call that the least upper bound, or the supremum. Likewise, there's going to be, well, it doesn't have to be, but there most likely is going to be a greatest lower bound as well. In this case, it'd be 0, and that's called the infimum. They are unique, if they exist. Supremum, infimum are unique. They're important because it's proven, and it's beyond scope of this course, but it's proven in a real analysis course, that if your sequence is increasing and has a supremum, then that's the limit. The limit is your supremum. If it's decreasing and has an infimum, then your limit is the infimum. But again, that's well beyond the scope of a Calc 2 course. That'll be real analysis, which I think you said you're a math major, you're going to have to take. Have fun. What do we mean by monotonic? There's two things. We say that the sequence is monotone increasing. If a sub n plus 1 is greater than or equal to a sub n for all n. Right? So the terms, each successive term, is at least as large as the previous. That's what it means to be monotone increasing. Right? Monotone decreasing is just the opposite. Right? Each successive term is no larger than the previous. If it's one of those two, monotone increasing or monotone decreasing, we would say it's monotonic. Right now, technically speaking, for the monotone convergence theorem, if your sequence is increasing, you really just need to show there's an upper bound. Then it converges. Decreasing, you have to show there's a lower bound, and then it converges. Because remember, n's going to infinity, so we don't care about the first terms. We only care about the later terms. Oh, and by the way, for this theorem, it's good enough to show that it's monotone increasing or monotone decreasing after a finite number of terms. Right, so the first, let's say 100 terms can be doing whatever, as long as it's monotone increasing or decreasing beyond that point and bounded, it's going to converge. Because again, we don't care about whatever it does in the beginning for the first 100 million terms. We don't care. What does it do as n grows infinitely large? I hate group chats. So we're going to show that this sequence is convergent. If you're to try to do this limit by hand, fun. I just happen to know how that function behaves, so I know what that limit is. I can just look at it. Limit 0. But what the hell is that symbol? So what the hell does that mean?
Just like multiplication of every digit of the number. It's like 5, and then the symbol that is 5 multiplied by 4 by 2.
Not that symbol. That would be that. Right, that's factorial. So n factorial, n times n minus 1 times n minus 2 times n minus 3, so on. So 5 factorial would be 5 times 4 times 3 times 2 times 1. That is known as double factorial. It's very similar. Except it's every other term. So if you did 5 double factorial, it would be 5 times 3 times 1. To show that this converges, we're going to use the monotone convergence theorem. So we want to show that it's bounded and monotonic. First, let's show that it's bounded. So 2n minus 1 double factorial. I'm going to write in the reverse order. Right, 2n minus 1 is odd. So it's going to be the product of all the odd integers up to 2n minus 1. Right, so 1 times 3 times 5 times 7 times 9 times 11 and so on and so forth. 2n is even. So 2n double factorial would just be the product of all your even integers up to 2n. What's important to note is that you're going to have the same number of terms in both numerator and denominator. What do you notice about each of these terms? 1/2, 3/4, 5/6. Right, your next one would be what? 7/8. 9/10. So on and so forth. Each term, isn't it less than 1? That entire product is going to be less than 1 times 1 times 1 times 1 times 1 times 1, n times. the sequence is bounded above by 1. 1 is an upper bound. It's always going to be larger. It's also fairly obvious that that sequence, 2n minus 1 double factorial over 2n double factorial, is always going to be positive. So 0 is going to serve as a lower bound. Hence, our sequence is bounded. Now I just have to show that it's monotonic, either increasing or decreasing. Well, to do that, consider the n plus 1 term. Well, that would be 2n plus 1 double factorial over 2n plus 2 double factorial, right? Just replace n with n plus 1. But notice something. Two n plus 1 double factorial is just 2n plus 1 times 2n minus 1 double factorial, right? 2n plus 2 double factorial would be 2n plus 2 times 2n double factorial. But this term here, the 2n minus 1 double factorial with 2n double factorial, isn't that s sub n? But this value here, 2n plus 1 over 2n plus 2, is that not smaller than 1? Which means the n plus 1 term is less than the nth term. This is a decreasing sequence. Specifically, it's monotonic. Sequence is monotonically decreasing. It's bounded below, so it must converge. So since Sn is monotone decreasing and bounded below, it converges by the monotone convergence theorem. Finding out what it converges to, like I said, generally is a whole other process. What about n factorial with 2 to the n? They say we want to show that this is divergent. Here's how we're going to tackle this one. We're going to show that a sub n is increasing, but has no upper bound. Well, if there's no upper bound and it's increasing, it can't converge, it has to diverge. Right? Because your terms keep getting larger without bound. So let's start by showing there's no upper bound. So if we look at n factorial over 2 to the n, n factorial, right? 1 times 2 times 3 times 4 times 5 times 6 times 7 up through n. 2 to the n. It's 2 times 2 times 2 times 2 times 2 times, right? N times. We have n terms in the numerator, we have n terms in the denominator. No, not 2 to the n, just n over 2. This would be larger than n over 2. Whenever n is larger than 4. Definitely does, well, yeah, definitely doesn't work for n equal 1. You get 1/2, 1/2. Doesn't work for 2. You get a half versus 1. For 3, you're going to get 3/4. That's not larger than 3/2. At 4, you're going to get, what is it, 3/4 times 2, which is 6/4. Is that larger than 3/2? Might actually, I think it is. No, I'm sorry, that's not larger than 2. That's right, and it's 4. But now if you go to n equals 5, 5/2 is larger than 6/4 times 5/2. And it's guaranteed every term after 5 as well. There's no upper bound. That means that no matter what term you're in your sequence, beyond 4, I can find a larger term. matter what we try to say the largest value is, I can find one that's larger. Now I just have to show it's increasing. Increasing without bound, done. It's going to be a similar argument as what we did over here. Look at Sn plus 1. So n plus 1 times n factorial over 2 times 2 to the n, right? That's how that would simplify. But this is going to be why did I do s? Should be a. But the n factorial over 2 to the n, that's a sub n. So we have n plus 1 over 2 times a sub n, which is larger than a sub n, whenever n is greater than 2. Whenever n is greater than 1. At 1, it would be a sub n. But then after that, this n plus 1 over 2 will be larger than 1. That proves that it's increasing, right? Each term is least as large as the previous term. Since we've now just shown that it's monotone increasing with no upper bound, the sequence has to diverge. Right? Each term of the sequence is getting larger and larger with no bound on how large that can be. So it can't converge. And yeah, we're just not going to do that one. That's proving the squeeze theorem. See if you can do it on your own as a challenge. Questions on sequences. Right. So at this point, you can now work on assignment number 16 on the MyOpen Math. Also, quiz 3. will be due on Wednesday. And so the quiz just covers what we've done since we've come back from spring break. Have a wonderful evening. See you again on Wednesday.